let's get started. So here's a little information about me. Been with the company for going on 2 years now, but prior to that, a lot of time as a consultant, and currently, in most germane to this talk, sanitary product manager. This is live updated. If you saw this last time, it was father 2.5, so I'm continuing to increment that as I get closer to having a third child. You never know, by the time we finish this, hopefully we'll have a third one. That's a picture of me. I updated this picture. I love this picture because that's me in grad school. That's waste right there, and I'm the one in grad school not wearing the gloves. So just bear that in mind through this whole talk. The guy who's not wearing gloves is the one who is now going to teach you about wet weather events. Here's our kind of recap and look forward. So we already did a talk just on the bare bones introduction into the world of sanitary sewer. We're going to just concentrate on wet weather today. And again, if you're just joining us, we have 3 that are going to be scheduled. They're each about 4 to 6 weeks out, so we'll do calibration later. Kind of obviously have to touch on that a little bit today, but try not to get too deep into those weeds. And of course, comment. So anything you've got, we can incorporate in the later webinars. That last webinar's validation will probably be kind of a catch-all validation and some other topics. So a little bit of review on the last presentation. There's a short link, like Nicole mentioned. We are recording these, so that link right there will take you to what you missed in the first one if you weren't with us, or if you just want to have a copy of it. A couple major comments that I would say I'm going to cover, as I promised on the last one. The first one was a little bit of a finger wag towards me for saying that minor losses were just minor. And so, yes, I would agree that perhaps a better way to characterize those are localized losses. And so if you're not familiar, minor loss is usually some decimal coefficient multiplied by velocity head. So while a lot of times in gravity sewer lines, you're at a really low velocity head, 2 to 4 feet per second, so it's not really going to have that big of an impact. Certainly for higher velocity areas or for force mains, if you're 8 feet per second, you could be having, a foot or so of hydraulic grade change. So appreciate that comment. That's true. 2 related questions, interesting that they're on both ends of the spectrum. One being, can a manhole have no inflow from a modeling standpoint? Of course, that's perfectly acceptable. It's not going to introduce any additional problems in a model. The question on the other end of the spectrum is, could a manhole have lots of different inflows? And of course, that would vary based on the modeling software you're using. But for instance, XP Swim, you could have virtually limitless dry weather inflows. Or wet weather. We'll cover that here. So that's kind of the quick review. Here's the agenda for this wet weather. So first we're going to cover the physical sources, and to keep this as interesting as I can for wet weather, I've adopted mascots for all the physical sources. So the slowest one being groundwater. And you could probably imagine what the fastest one's going to be. It's kind of hard to come up with a middle speed animal. So based on an internal poll, non-scientific here at XP Solutions, came up with guinea pig. So we're going to cover what infiltration looks like from a physical standpoint, and then inflow, right? So turtle and hare are easy to do. So from a physical standpoint, that follows the same general approach we used in the introduction. And then we'll cover the same on a modeling standpoint. Now, some of you may be asking, when I think wet weather, I'm thinking rainfall, derived, inflow, and infiltration, and we'll cover that in a second. So I'm wondering, maybe groundwater doesn't really fit because it's not quite the same. Well, we're going to bring it back and use it anyway because, 1, there's not really a better spot in this series to talk about it, and 2, it can really impact what happens, especially when you get into calibration. So we'll consider it, even though it's a different time scale, as inflow and infiltration. We're still going to cover it here. So let's talk about where wet weather can enter your system. I really like this picture because it can show you all the different areas. So you can see on the right side, and if you can see my cursor, some storm sewer specific areas. But certainly if you look over in this house, there's lots of areas, both intended and unintended, where wet weather is going to enter the system. A lot of those are through defects. You can see pipe cracks. Anything in red basically could be a problem. Notice again, this will be a theme you'll see throughout here. A lot of this is the residential area. So this is the private property, ends up becoming a problem. So any of these areas are areas where effectively stormwater is entering the sanitary sewer system. And we'll cover this again, but that's kind of the holistic overview of what we're trying to conceptualize into a model. So pragmatic modelers out there would all say, well, why do we care about that? Other than just trying to get the model to be accurate, what's the problem with wet weather flow? There's lots of problems. I'll just cover 3 general ones. The first being health and safety. So this is interesting. This is the quote-unquote flushables, flushable wipes, etc., and what happens when they hit a pump. So this is a lift station. So you can imagine if this lift station is overcome by too much wet weather flow, and you may or may not see in the background some kind of play structure from a school or otherwise. So obviously health and safety is a priority, and so you don't want overflows or malfunctions or flooding events. Even if that wasn't necessarily a priority for you, different regulatory entities can make that a priority for you through enforcement, direct enforcement, or heavy, maybe not absolutely direct, but it can really help you in your process. And typically this is wet weather related. And then the third one, the most practical one, I suppose, is cost. And a lot of times you think of cost from conveyance standpoint. I may need a bigger pipe or even bigger, smaller facilities, but certainly that also happens all the way through treatment. So this is a fairly large wastewater treatment plant in North Texas, slightly less than 200 million gallons a day, but I'm just going to circle a few spots in red that are specifically designed just to handle additional wet weather flows. On-site storage basins, headworks changes to pump stations, changes to the recycle water pump station, and of course all the actual line work in the plant. And then you have chemicals disposed. So it's really it can be quite a expensive endeavor. So there's lots of reasons that you want to be able to characterize it, and then at some point you'd like to be able to reduce it. So the first step is understanding the problem. So let's go to those physical sources again, and we'll start with groundwater. And if you go to enough technical presentations or academic presentations, and almost sometimes, especially if you have a pretty big groundwater concern in your system that you're modeling or that you're living in, it's almost like a tile drain that you didn't know you have. And if you're not familiar with the tile drain, it's more of an agricultural feature. So you can see here in section view, you have this pipe drain that's purposely perforated, and it's able to draw down the water table, which makes sense because the water would prefer to flow down a pipe than to percolate or infiltrate through the ground. So our sanitary sewer system is hopefully not perforated, but if there's enough defects, it can act that way. So what does that look like? Well, let's assume that we're looking at a cross-section of a sanitary sewer line. So a very simplified example. And so we're going to take that cross-section that's running down maybe parallel to a creek in your area, or maybe perpendicular to something else, and we're going to kind of turn it and look at it in section view. So now we're looking down the pipe. So we're standing in the pipe. Let's assume there's 3 of those pipes, and they're in 3 different vertical areas. And so one of those areas, the topmost one you see here, is basically going to be dry all the time. In this example, you can see that there's this intermittent saturation zone that will raise up in winter times. That could be induced by snow melt or just changes in more broader rainfall patterns. So that area in the top is always going to be dry or always not influenced directly from groundwater. Again, we're strictly talking groundwater here. The middle one you can see would change over time, and the bottom one would basically always be saturated. So you look at that a different way and say you have a no groundwater, you have a seasonal groundwater, and you have an always under the influence groundwater. I say that's a problem. Obviously, that's a problem from the standpoint of infiltration. So what might that look like as far as hydrographs? So this is a long duration, so assume this is several months of flow. So obviously dry is going to be 0, right? You'll have no flow under dry weather conditions. Here you can see what I'm calling saturated flow. Now this assumes that there isn't any industrial flows. If you are running something that's an industrial facility and it's an operation that runs 24 hours a day, obviously this isn't as applicable because you could be generating the same amount of flows all the time. But if you assume that you're predominantly residential, or you have at least a big part residential, it's highly unlikely that there are more than 2 million gallons per day all the time of people flushing toilets and running dishes, et cetera, et cetera. There's just not that many night owls out there. So you're going to get this constant level. That's kind of the saturated level. Well, the same thing you can see here, a slight variation of that is a really long and slow gradual increase and decrease. So some of the peaks are changed. It doesn't affect everything, but you can see generally speaking that, let's say in the winter and spring times, you're going to have a more of an influence, and then in the summer times it's going to be reduced. And certainly it's something to be aware of if that's something that impacts you, and there's lots of areas that have that, because if you don't take that into account and you start doing calibration or you start modeling over a continuous or a longer, a year or even 6 months worth of data, you're missing a variable and you might end up calibrating over that variable using something else, which is not ideal. What might that look like in, again, this physical idea? Well, if you can actually look into the pipe, it's going to be clear, relatively speaking, hopefully not as much of a quantity and non-turbulent. So here's just an example of what you'd expect, right? It's a relatively clear speed, and it's just kind of there. In fact, I've seen this before doing manhole inspections in brand new neighborhoods. You go to a brand new neighborhood, all of the lines are built, but there are no houses, or there's a few houses, but no one lives in those houses. And you pull the manhole cover and you see a third of the pipe flowing full of water. Well, that water on a nice, bright, sunny day, and it's been sunny in Texas all through the summertime, is coming from groundwater. So that's something that you're treating, but you also need to be able to capture what's happening. Okay, so now let's switch gears a little bit, and now we're talking about something that's directly related to rainfall. So what we talked about before is obviously there's a relationship to rainfall. You're not going to find groundwater in the desert, right? So you need to have some rainfall to establish what's happening, but now we're talking about things that are directly related. The first one being infiltration. So here's an example. You can see where infiltration can get into the system. And so you see some root penetrations in this lateral. So basically a leaky lateral feeding into the main system. Again, that's a private property issue. You also have some broken or cracked pipes or joints that are off. The manhole, the base of the manhole may be broken. These are all things where rainfall can work its way, basically infiltrate its way into the system. But it won't be quite as the same as inflow, which we'll cover in just a second. So what might that look like from a hydrograph? Well, in this example, infiltration may be happening right in this area. And so you can see at the top there's some rain hydrograph. There's a little bit of rainfall depth, and there is 1 or 2 days later, you start seeing a difference. So you can see between 0 and 1 days, it's basically no difference. It's the base flow, but then over time, a slightly delayed time, you're obviously seeing a response that is directly related to inflow. It's going to be more turbulent wherever it enters. Again, you're assuming it's going to be clear, and you may have a larger volume. So here's a couple examples of the lower one is in a manhole, obviously, and the other one is in the pipe itself. So you see water squirting in through some type of defect or misalignment. And then you have inflow, which is similar, but basically the biggest difference being that inflow is a direct connection, whereas infiltration has to do a little bit of meandering, so there's some flow attenuation. And I guess if you had 1 inch of rain, that's inflow versus infiltration, you also have not only the attenuation or the magnitude, but the total volume would be less. So here you see this roof leader connected to the sanitary system. So if you're having flooding issues at your house, rather than trying to build French drain or build a way to daylight it, you just connect it illegally to the sanitary system. That's obviously going to collect all the rainwater from your roof and put it right into the system very quickly. You may be doing it, though, not intentionally. So a lot of houses have sanitary sewer cleanouts that are covered with kind of a relatively inexpensive gasketed piece of material that will degrade over time or be buried under landscaping. Perhaps if you see in the street view here, you may have a manhole cover that leaks. So you may do dual drainage. So your road may also, by its design, carry some of your stormwater. Well, if the manhole doesn't fit right or the pick hole goes through and through, you're obviously going to get some direct inflow into your system. Now there are other ways to address that. There are rain guards and there's some structural ways to fix that, but it certainly could happen. So going back to the picture before, I think you may be able to guess where the inflow would occur, right? And so it's in this case, it's going to be the much higher magnitude response and a faster response. It's a somewhat stylized example because obviously there's a lot more rain occurring back to back to back. So it's not, absolutely perfect, but you can see again the difference, right? So this inflow would have infiltration and inflow in it, but you can see just a much higher response back. As you can imagine, it's going to be very turbulent and potentially a lot of volume. Here's an example of smoke testing. In this case, you basically inject smoke into the sanitary sewer system and see where it comes out. Anywhere it comes out is an area where rainwater could come in. So in this example, if that's a clean out, they've marked it with a little flag, that needs to be covered, because if it rains, any little overland flow or direct flow will go right into the system. And what might that look like in the system? Well, the lateral may penetrate, in this case, at maybe 2 o'clock, and put a lot of flow in. So that is direct flow and a large quantity of flow all in at once. So those are the three main culprits we're going to cover: groundwater, infiltration, and inflow. So let's talk about how we're going to model that, right? It's one thing to know that they exist. A lot of us know that. We kind of have a little idea of what those things are, but how are we going to model that? So you may say, well, there's going to be some one-size-fits-all. Well, coming directly from the EPA, and I'll paraphrase, there is no RDII method that's universally applicable because everything is different, right? So an RDII, again, is rainfall, derived, inflow, and infiltration. So you can't really pick one method that's going to do everything. It's just not a one-size-fits-all method, but that's okay. We can cover some different methods, and that's what we're just about to do. Before I get into that, there's a couple methods, I will say they're methods, that I would not encourage you to use unless you have to. Now, there's always a reason, there's always an exception, so by all means, I'm not saying these aren't applicable, but if you can avoid them, the two of them are kind of the decibel multiplier method and then like a second persistent pattern on top of dry weather flow method. If you can avoid those, that's ideal. So the decimal method is what I call the it's not believable approach. And the second persistent pattern is kind of the, it works 100% of the time, 20% of the time. Or, you know, a broken clock will be exactly right twice a day type approach. So the decimal multiplier is, I have some value. It may even be a historical contexted value. So perhaps I know that my wastewater treatment plant or my outfall meter under a big event registers 4 times as much flow as average daily. So my wet weather is 4 times greater, and we all like numbers, and we all like to have something distilled down into a value. So we say it's a 4. So then I will just take my average daily flow in the entire system and multiply it by 4, and that will be my wet weather. There's a few reasons that's not ideal. Again, there's reasons that you may have to do that, but there's reasons that's not ideal. Principally, if you're just multiplying it by a number, even if it's not completely arbitrary, you're not able to determine anything about the volume of the flow. So that means you can't really make any kind of assumptions on the system storage or anything that happens in any of your facilities. And you also can't make any future considerations. In other words, it's not tied to anything physical. I'm going to multiply it by 4, whether it's 2 inches of rain or 10 inches of rain. It's just a number that's there. So the persistent pattern is a slight variation where I have something that does vary over time, which means that volume and storage I can handle to some extent. Again, it's not tied to a specific rainfall event, so I'm really left to just validating the model. So I can't make any future, what might happen in 10 years, what might happen with this change in pipe material. And I can't do a lot of timing, but it's slightly better. So those are 2 that we're not going to cover. They're really all extrapolation problems where you have 1 or 2 little bits of data, and then I'm trying to see what might happen in 5, 10, 20 years from that 1 or 2 pieces of data. And that can be very problematic, especially, a lot of these models are tied to fairly large capital decisions. So, I mean, obviously there's a lot of logic involved and there's a lot of engineering, but the model is one data point there. So you really don't want to have it projecting a really big pipe or really small pipe without something more physically based. Okay, so modeling groundwater. So if you are a hydrologist, I apologize, you're not going to like my pseudo water cycle, but I'll say this, that rain either is going to, water will fall out of the sky or already be on the ground in some aspect, and that's on one side of the equation. What happens to that water? Well, it can be evapotranspirated, so it can disappear back up into the sky. It can infiltrate or percolate down into the water, into the water table, into the groundwater. It can be runoff or it can be outflow / storage. In other words, it can stay in the pond, right? So a very simplified approach. So if I just highlight the red things there, infiltration and outflow, those are the 2 ways that you can end up affecting the groundwater table. And that's what we're trying to do, is affect the groundwater table to determine what flow might actually leave the groundwater table and enter into our system. So I take those concepts, the real rough conservation of mass there, and I look at something like XP swim. Well, you can see those same things are here, right? So evapotranspiration is a variable, the infiltration and percolation is a variable, how groundwater might outflow the system is a variable. What else happens from a groundwater standpoint is not really that important. So if it stays and it moves down the river, it's not really something that affects us from a groundwater standpoint for sanitary. So let's dig into what these look like on an individualized basis. So first off, you have the evapotranspiration. Well, again, you can see here, wilting point, field capacity. These are all things that are physically based. These are things that you could test, or certainly you could determine some parameters to help bound your expectation there. Same idea with infiltration and percolation. So you have hydraulic conductivity, and you have ways to determine your losses through percolation. Now note, you're already at about 10 variables. So we're starting to add more and more variables because the process is not necessarily simple, right? So it's not overly complex, but there's lots of different variables that can impact what happens in the system. And the final thing, of course, is the actual outflow itself. So how does flow leave this boundary condition? So now we're up to 15 variables. Bear that in mind if you're trying to, calibrate. If I can foreshadow into the future, if you're trying to calibrate that, there's a lot of different things to change. The last thing here is the boundary condition. So you can use a constant boundary condition, or you can actually vary it based on the conduit depth. So remember back to our physical idea. Well, obviously, if your groundwater table is at 200 feet below ground and your pipe is 15 feet below ground, perhaps you don't need to worry about groundwater to the same level as someone whose groundwater table can reach almost to natural ground and their pipes may be 20 feet below ground, and that may change over time. So the level to which you would use groundwater and how you'd use this kind of interface would vary. But another thing that people will do once you do the effort, if you go to the effort of calibrating it, it's kind of a brilliant approach, I would say, is if it's applicable to you, is you have typically historical rainfall data stretching back decades. You don't have flow data, so you just have rainfall data. Well, a lot of modelers will choose to run, say, 50 years of rainfall data before they ever even worry about what's happening with the actual flow, and they'll become quite good at fine-tuning the calibration, fine-tuning the groundwater depths. Perhaps they have monitoring wells, etc. So they do a lot of pre-work to even getting to the point of doing infiltration, inflow analysis. And that's part of the reason that I wanted to include groundwater here. So modeling infiltration. There's a couple ways to do that, and the method I'm going to show you here is the RTK method. And so RTK stand for 3 parameters that we're going to cover. The first one is R, and R is the fraction of rainfall from what falls out of the sky that gets into your system. So the simplest way to think about that is a higher R is going to make whatever your triangular hydrograph, it's going to give it a higher peak. The value is going to be higher. And if you're not someone who does a lot of hydrology, these are standardized unit triangular hydrographs. So you need an R to figure out how tall the hydrograph is going to be. And then you also need a T, and this T parameter tells you how long it takes to go from rainfall event to peak. That makes a difference too. And then the final thing is kind of this final shape in the triangle, which is this ratio of lead arm to lag arm. So what that might look like. You can see in this example there's a total, which isn't a hydrograph anymore, but a different polygon shape, and that's made up of 3 different responses: a rapid, an intermediate, and a long. So if you've not used this before, you may be able to think ahead and say, well, even though I'm talking about infiltration right now, if I had a really big rapid response, that would probably be inflow. And if I had a really, really long response, that may not be groundwater, but it may be like a really slow percolation. Not an impact from the groundwater table, but definitely a slower impact. And you would be right. So certainly you can do that. So you can use this method both for inflow and infiltration, and in fact concurrently, and a lot of people do that. But just for the purpose of me talking about infiltration, I'm covering it just the RTK method. Now I did I don't know, maybe 45-minute talk just on a program called EPA SOAP. I believe that's the sanitary sewer overflow analysis. It's a toolbox that EPA put out. It's a free piece of software. So if you use that link, you can go to it, and it's 45 minutes of me talking through how to use the software, because the software works great, but it doesn't have a lot of user guides or tutorials. It has nothing to do with XP Swim. It's just kind of our helpful guide to you to know how to use it. And what this toolbox will do is help you calculate this RT and K. We'll cover that in just a second, the next slide, of what that looks like. But just because I don't have the time to go into too much depth, but I want you to have some tools to be able to help. So there's about a 45-minute talk just on that. After that, there's actually another talk, maybe half an hour or so, on how you could use EPA SOAP with XP Swim. So we do talk about some workflow methods for how to interface the two, but you'll get just a talk on one or the other. So by all means, use that. So again, if you're very pragmatic, you may say, so for short term being like one single event, that makes a lot of sense. But what about long term? In other words, if it rains 1 inch today, and then it rains 6 inches tomorrow, well, I would intuitively expect that system to respond different than if it just rained 6 inches tomorrow, right? And so that is this problem of antecedent moisture, right? Big issue. So we have a way to fix that with the RTK method. And I bet you didn't wake up this morning expecting to see a superhero guinea pig. So if you did, you should email me, because I'd like to hear about that. But we do have antecedent conditions. So basically what we're doing with antecedent conditions, or we're trying to handle that. So if we treat the catchment, or the area that we're trying to apply all this to, as kind of a reservoir, then we know, like, do we have initial abstraction? So how much water is going to run off versus stay? How much can we store? How quickly are we depleting that storage? So we have some way to be able to run a more continuous simulation, which is really important. If you don't do that, and I think everyone's been there at some point in their career, you end up with really strange looking graphs where you have 1 inch of rainfall at even maybe the same intensity, that inch of rainfall producing a bigger response from the system than 3 inches of rainfall. And that's really hard to explain if you don't have a way to handle these antecedent conditions. What that looks like in more practical terms, and this is again a screenshot from XP, is you've got the R, the T, and the K. So that's that fractional rainfall, the time to the peak, and that ratio of recession for short, medium, and long. Those are the columns. And then you have these abstractions in storage and recovery rates of storage, again, for short, medium, and long. Basically, once you determine what those values are, and it's kind of nice, it's a parametric way to determine what happens. Once you determine that, you can attach a rainfall to it. If you add in your sewer shed area, you're good to go, right? So if you have that, and let's just assume I wave my magic wand and it's calibrated. Well, now, versus the methods we talked about not wanting to use as much, different rainfall events, the model will respond differently because it's more physically based now. You will get different RT and K values for different rainfall events because they will still respond differently. And that's, again, something that EPA SOAP will handle well, which you do some generalized statistics to determine what those values should be. So inflow, again, you could use either one of these interchangeably, but let's talk about a different way and apply it to inflow. So I kind of mentioned before in the groundwater example, if you're a hydrologist and you're really good at the water cycle, well, it's kind of tough for you to be really good at the water cycle and then have to go switch over to this parametric RTK thing, right? So now you're very empirical, and while it's been around for a long time, it's not the same as some of these equations and approaches that have been around and you may be more comfortable with. So is there a way we can do that? And the answer is yes. And this is really good if you're doing like a dual master plan. And by dual master plan, I mean if you're doing a stormwater master plan and then a sanitary sewer, and I don't mean they have to be concurrent. If you did a stormwater master plan last year, someone invested a lot of time into determining how the rain is falling out of the sky and how it's being routed. So there's a way that you can use some of that rather than just reinventing the wheel. Also, if you know the way that some of this inflow occurs, in other words, you do know you have dual drainage and you do know the extent of where the problem areas are a little bit better, then this is a really good idea. Basically, it's relatively straightforward, especially once you have the hydrology done. So you determine how the rain, where the infiltration is, and how everything is routed. So you go through that effort, and so if like an XP Swim, you might pick any of the 20 or so different methods, and you've kind of honed in and nailed it exactly right. You're able to really finally discretize your subcatchments, so you know your area and your impervious, you're kind of lining everything out. And then you do this nice final step where you just say, I want to interface some of that flow from my runoff to my hydraulics. And so kind of a loose corollary would be like, this is the R from RTK, but I'm using all of my routing methods to better determine the T and the K. And then I'm attaching the R value by saying for this specific node, this specific amount of interface. So this is a 5%. So 5%, whatever happens, is going to interface in. And then you can further route it through your hydraulics. So there are other methods out there that I just, in the interest of time, didn't cover. One of them is, what I've seen before is the antecedent moisture method, which is kind of a parsimonious method. So basically saying I can take other physical parameters, say not just rainfall but temperature, and I can come up with a good predictive model based on that. You also may have a really long polynomial kind of trailing moving average method, which is more of a statistical inference on what's happening. Or you may have your own localized empirical method, right? So perhaps you have something either you developed or you were told to use that works for your area really well, because we all know that Central Florida is going to act different than Eastern Oklahoma. So you may have your own method there. In fact, I'm interested in knowing what methods you do have, and to keep some of you awake, I'm going to try to launch a poll on what methods, see if we work there, yeah, what methods you use. So I put a few in there, right? I've covered some of them, and then I have a big box for other. So go ahead and take a minute and vote if you can. You can vote, you should be able to vote more than once, just on what you use when you're tasked with doing a wet weather analysis. All right, enough people have voted. That'd be a passing grade in one of my grad classes, so I'm going to close it now. And let's see if I can share it. Hopefully you can see that. So it's kind of what we'd expected. It's a good collection between RTK and hydrology, with a lot of you using the multiply and pattern, and some of you needing to use groundwater. Excellent. So let's take kind of a step back. So we've talked about, I kind of went right into how to calculate this on a pretty specific, node by node level, right? And so you remember this graphic where we see all these different places where flow from one house could enter in. So let's think about that in a different way. So this is all conceptual, but I think you'll get the idea. Let's assume this is your municipality or village, and we have some large diameter trunk lines that are moving from east to west. So you don't see all the small laterals or even the collectors, it's just the bigger lines. And let's say that you are fortunate and you have enough fee in your project or your study to put a meter on the end of each one of these lines, right? Lucky you. Well, each one of those has like a meter boundary, a sewer shed or meter shed boundary that I've shown here, this polygon. So that may be where these areas are captured. Well, let's hope that you also have the fortune to have a lot of rain gauges. So I've thrown some rain gauges in there. In fact, I don't really cover it here. I'll cover it more in calibration. Lack of rain data is one of the biggest problems when trying to calibrate. So it's not really possible to do an RTK method and be able to come up with RTK values without rainfall associated with it. And from my experience back as a consultant, the first thing that get axed in the contract is rain gauges. But let's assume, for this sake, we have rain gauges and they're located in all over the place and they're good data. That's great. Well, again, we have this concept of manholes spread out all the way upstream of these meters, and all those manholes are going to have lateral connections and they're going to have collector lines to all of those structures, right? Pretty much any of those is going to create dry weather flow, which means that that's an entry point for wet weather flow. So we go from feeling really good about ourselves with all these meters to all these potential entry points of flow. And that's what I'm calling the big problem. And so on the right, you see a stylized version of attenuation. The bottom one here is kind of my favorite example of the wastewater treatment plant effluent. It's really, really constant. And as you move up through the system, you begin to become less attenuated, more spiky with what's happening. And so as you kind of aggregate downstream, it changes. So let's assume that some of you have more than one treatment plant or outfall, but let's assume if you do, you just pick one. Pick your favorite. Everyone has a favorite. So pick your favorite plant or outfall, and let's assume that you have a variable B. How many gauges exist in that outfall? So in this example here, let's say that it's 3. There's 3 gauges that are measuring flow, or meters, and measuring flow into this outfall. Well, for every one of those gauges, there's this I, the number of entry points. So that could be manholes, it could be laterals, right? Those are all entry points, and there's a lot of those. But there's this G variable, source points, for every entry point, right? So we know B, we theoretically have data on this gauge, let's hope, but we don't know the big, the BIG, right, which can almost be infinite. So that could be daunting, right? So what are we going to do? How do we keep that from being a really big problem? In fact, there have been some studies out there, and we've done our own surveys saying, like, how big of a problem is this capturing our wet weather? How big of an issue is this in your project? So I have one more poll for you, and the question is, what % of your project, I'll launch it now, what % of your project is related to figuring out wet weather? So don't worry about calibrating dry weather. Well, it's not as hard. If you're thinking on a fee basis or effort basis for you specifically, how much of that is related to just the wet weather devilry of sanitary sewer? All right, I'll close it and let you see it. It's a pretty good split, actually, pretty much all around the board. So for some of you, it's not that big of a problem, and that may be because your system is well built. It may be because that's just not something that is the focus of the project you're working on. It could be lots of reasons, and then it kind of ranges all the way up to, hey, this is a big problem, just trying to determine what it is. And this is unrelated to fixing the problem. It's just trying to determine the problem itself. Okay, so I'm going to try to give you a little bit of practical advice if I can. Easy for me to say, right? No longer having to do these, but let's give some advice. And so the first thing I'm going to do is just a flow chart I sketched out on how I would approach one of the biggest problems, which is determining the focus of an individual area. In other words, let's say I love RTK and I'm going to apply it everywhere. Well, what does everywhere look like on, say, an RTK basis? Because what we don't want is we have a meter flow of 2 million gallons per day, and so we attach 2 million gallons per day only at the downstream end. Well, that's not going to work, right? That gives no flow all the way through the line. We don't want to put it on the upstream end because that's going to be really way too conservative, because a lot of that flow occurs throughout the line. So what do we do? Well, here's what I would do. So the first question I would ask is, can you subdivide the area? So back to our stylized example, if we have a meter, then sure, you can subdivide that, right? You could make a meter basin. There's a yes and no there. If you can't, then you should stop, right? If you can't make it any smaller, realistically speaking, then you've reached the end. But let's assume that you can subdivide the area. The first question would be, can I estimate flow at this level? I'm not asking, do I know the flow? I'm just asking, is there a reasonable way for me to estimate it? A lot of times you'll just say no. So that's why you don't have necessarily catchment areas that are to the individual house, right? Like there's no real way on an hourly basis through a day to estimate a flow there that's going to make a difference. That's really not a good use of your time. So then the question would be, okay, I can estimate flow. Is that flow tied to rainfall or not? Like specifically rainfall. So it may or may not be. And so let's say it's not. I just can, through my intuition, I have an idea what the flow is, or I have some data but I don't have a rain gauge, so I just kind of have an idea. Then I would ask, are you just validating the model? If you're just validating the model, that's great, right? So you totally can use the model and you can compare it to something that you know or you think you know through a couple observations. I would say go ahead and do that, but just be aware of the limitation, and then you're back into the cycle of, can I re-subdivide the area or not? If you're trying to do more than validate the model, I wouldn't do it. I would just kind of use my effort somewhere else, because you're really not going to be able to justify the extra effort, because invariably, if you're to that level, you're going to have more effort. So is it physically based other than rainfall would be the last question I would ask. And so there's two options, of course. So if it's physically based, like if I have some physical reason for knowing that, so in my easy example here, a sewer basin tied to a meter is obviously physically based. I should totally do that. I should totally subdivide it to the meter basin and then consider subdividing it into something smaller and flowing through this flow chart again. If it's not physically based, so it has some reliance on rainfall, but there's nothing else really physically based on it, I would probably do it, but I would be really careful about conditions. And a lot of times what I mean by that is, if I don't have any way to tie the the amount of flow that I expect to see to something, what's a good example? If I don't have it based on, say, number of manholes or the type of pipe or the condition of the pipe, I will still get a good answer for existing conditions. But if one of my projects in 5 years is to slipline that pipe, how am I going to make a change? I need to be very careful because I've changed the physical conditions of the system, and that would necessitate a change to how wet weather interacts with my system, and I haven't built in a way to handle that. So it's just something to be mindful of. And again, I would just continue to cycle through this over and over again. Once you've reached a point where you really can't divide it logically or practically any smaller, then I would say, all right, I know what the different factors are, either through hydrology or through RTK. I need to be able to calculate what they are. So practically speaking, what does that look like a lot of times? Well, in the simplest forms, it would be some type of geometric application, like a Thiessen polygon, Voronoi polygon application of manholes based on sewer flow. So if I have a meter and it's 5 million gallons per day and the land use looks the same, then I might just break it up based on area so that I can attach it throughout the system. And that way I'm putting flow in through all the different manholes, and it's somewhat physically based because obviously if the land use changes or someone adds a new pipe, it's going to change what happens there. But it's a good start, and then I probably can't divide it smaller unless I have a program to handle that. So final advice on that is if your project is bounded on two ends, on the left end is what I'm calling the physical limitations, and on the right end, the error limitations. There's two spots you don't want to be, and that's shown here in the red. And so if you're outside of physical limitations, that's just bad judgment, right? And that happens to everyone from time to time. So that might be an example where if you did take the R value from your RTK, or you just took the magnitude, the peak value, it was either a 0, so there was no wet weather infiltration or inflow, or it was like a 50, and you have no data to support that. Well, you're outside of just physical, logical, what's supposed to happen. So we don't want to be there. So we want to make sure we at least get to something that's reasonable. That's again why sometimes the decimal multiplier will work, sometimes it won't, because it just depends on the physical limitations. But you also don't want to be in kind of bad logic land past what error limits are. So of course there's error limits in a meter. So if you're paying a vendor or you have your own meters, you'll have a small error on the actual meter itself. Not only what it's reporting, but exactly what the hydraulics are in the area. It's a small number, but consider, let's say again that we have a wet weather event that's shown to be 10 times, peak on that day what dry weather is. Well, by its very definition, we kind of have an error of 10%, right? Because if that happened to occur during peak dry weather flow, the total flow is different than it would have occurred during a regular event. And so if you're really trying to really get down into the few percentage points, and this kind of bleeds into calibration, but you're starting to not really realize gains. Like you might be able to find gains in other areas rather than trying to really get fine-tuned down in the error limits. So you're going to live somewhere in between, right? And that varies all over the map. And that's really a function of how much effort you have and how much time you have to spend on the project. It varies on your experience, the strategy you take from the beginning. Lots of variables affect where you are. And again, so that's why you may be down on a project that's kind of closer to physical limits. And you're running decimal multipliers because that's what you need to know. And you may be on one that's up to error limits based on your capabilities as a firm or as an individual or based on the project needs. At the end of the day, bring back our lovely mascots. I'm telling you, groundwater is slow. So the sources are going to vary, right? Hopefully we've made that clear. The sources into your system vary throughout your system, let alone your neighbor's system. The requirements, so the non-physical requirements, it's just the requirements of the project, otherwise they vary. There's a variable there, which means your solutions will vary. And even within the individual solutions, kind of the concept of like your mileage will vary. So hopefully I made some of you happy, or all of you happy some of the time, right? I'm sure some of you wanted some more specific deep dives into executing a model. Well, the problem is, get back to the EPA quote, we're just not going to be able to affect everybody the same way. But we do have other features out there. So if you're current and you're in the knowledge base, we have knowledge base articles, for instance, on, well, RTK is 9 variables. I bet I could come up with 2 completely different collections of RTK decimals and get the same value. So is there a best strategy? Well, there is actually kind of an industry standard strategy. Well, you know, that's something you can see. Are there other specific questions about your problem, not necessarily the method or even the implementation, but how your actual project, well, that's something else we can look at. And of course, again, the biggest mountain to crest, if we're kind of looking at it, is calibration, right? We do all this work and all this effort of trying to determine how to do it so that we can verify that it actually works. So the next one, the third in our series, has kind of been building up to this idea of how are we going to calibrate a model? Because again, if we're going to generate a CIP that's $5,000 or $500 million, a lot of it's going to be based on the hydraulic performance. So what do we expect to happen? What's our level of service? Well, all those things kind of hinge in part on having a model we have confidence in. That's what we're going to cover next. So that's the end of this one. I haven't been able to jump on any questions. Some have come in. If you have others, just hold on a bit. And after we close this down, we'll stay online to answer those. If you don't have access or ability right this second, by all means, drop me an email. That's where some of the comments from the last one went, and I will answer them. I appreciate everyone's attendance, and I appreciate everything to do with the sanitary sewer system, and I'm looking forward to the next few webinars here in the next coming months. Thanks again.